Hello everyone, welcome back to Eccentric Cosmos, where we explore the fascinating world of science. Today we will be talking about one of the most mysterious and intriguing objects in the universe, the black hole. In this video, we will learn more about this mysterious object's origin and effects on nearby matter, as well as why they continue to captivate astronomers, physicists, and the general public. Black holes are formed when a massive star collapses on itself. When the fuel in the star runs out, it can no longer generate enough energy to hold itself together, and its core collapses into a point of infinite density known as singularity. The gravitational pull of this singularity is so strong that it creates a boundary around it, known as the event horizon, where not even light can escape. A star is formed from a cloud of gas and dust. The pressure and heat generated by the star's nuclear fusion reactions cause it to expand. Once the star begins to fuse hydrogen into helium, it enters the main sequence phase and begins to shine brightly. This phase can last millions to billions of years, depending on the star's mass. When the star runs out of hydrogen fuel in its core, it begins to collapse and heat up. This causes the outer layers of the stars to expand and cool, turning it into a red giant. As the star continues to lose mass, it will shed its outer layers, forming a planetary nebula. The inner core of the star will continue to collapse and heat up. If the star's core is not massive enough, it will eventually become a white dwarf, which will slowly cool and fade away over billions of years. When the core of the red giant becomes unstable, it collapses, leading to the formation of a white dwarf, neutron star, or black hole, depending on the mass of the core. If the core mass is greater than about 3 solar masses, the collapse continues, and the core becomes so dense that its gravity becomes extremely strong, forming a black hole. If the star is huge enough, the white dwarf won't be able to resist the core's gravitational pull and will continue to disintegrate until it forms a singularity, a point of infinite gravity and density. The star will turn into a black hole as a result of the singularity's gravitational attraction, which will form the event horizon as a barrier around it. The Chandrashekar limit is a theoretical upper limit on the mass of white dwarf star, beyond which the star will no longer be able to support itself against gravitational collapse. It is named after Indian astrophysicist Subramanian Chandrashekar. The limit is approximately 1.4 solar masses, and any white dwarf with a mass above this limit will eventually collapse under its own gravity to form a neutron star or a black hole. The Chandrashekar limit is determined by the pressure and density of electrons in the white dwarf, and is based on the principles of quantum mechanics and special relativity. The Chandrashekar limit is an important concept in our understanding of the evolution of stars, as it helps explain why some stars end their lives as white dwarfs while others become neutron stars or black holes. The singularity is the point at the center of a black hole where the density and gravity are infinite. This is where all the matter that enters the black hole is believed to be compressed into a single point. The event horizon is the boundary around a black hole beyond which nothing can escape, not even the light. It marks the point of no return, where anything that crossed it is pulled in by the black hole's gravity and cannot escape. The accretion disk is a ring of gas and dust that orbits the black hole and is pulled in by its gravity. As this material is pulled in, it heats up and releases energy, creating X-rays and other forms of radiation. Some black holes are thought to produce powerful jets of material that are ejected from the poles of the accretion disk. These jets can travel for millions of light years and are thought to play a role in shaping the evolution of galaxies. The shadow of a black hole is a dark area that is created by the bending and the distortion of light around the event horizon. The shadow provides a way to observe and study black holes indirectly, even though they are invisible to the naked eye. Black holes can also generate gravitational waves, which are ripples in the fabric of space-time caused by the movement of massive objects. These waves provide another way to study black holes and learn more about their behavior and properties. There are three main types of black holes: stellar, intermediate, and supermassive. Stellar black holes are formed from the collapse of a single massive star and can range in size from a few miles to several tens of miles. Intermediate black holes are much larger, ranging from hundreds to tens of thousands of miles, and are thought to be formed from the merging of multiple smaller black holes. Supermassive black holes are the largest, with a size of millions or billions of miles, and are found at the center of most galaxies, including our own Milky Way. Black holes skews space-time by exerting a massive amount of gravitational force. According to Einstein's theory of general relativity, the presence of massive objects like black holes cause the fabric of space-time to curve and bend. The bending of space-time creates what is known as a gravitational field, which attracts other objects and affects their motion. When an object is near a black hole, the strength of the gravitational field is so strong that it can cause the object's trajectory to bend and curve, as if it were being pulled it by an invisible force. The effect is known as gravitational lensing. As an object moves closer to the black hole, the strength of the gravitational field increases, causing the object's motion to slow down and eventually stop. At this point, the object is said to be frozen in a place, and the only way it can move is to be pulled further into the black hole. The skewing of space-time by black holes is what makes it possible for them to capture and hold onto matter, even though the matter is moving at high speeds. The gravitational pull is so strong that it overcomes the matter's natural tendency to move in a straight line and instead causes it to follow a curved path into the black hole. The death of a black hole is little more complicated, as there are different theories about how it can occur. One theory is that when two black holes merge, they will eventually merge into one single black hole and losing energy through gravitational waves. Another theory is that when a black hole can shrink and eventually evaporate over time through a process called Hawking radiation. Scientists still don't fully understand black holes, which are incredibly fascinating things. We may learn more about the creation and death of black holes, as well as the part they play in the evolution of galaxies, as we continue to explore and study the universe. Thank you for watching the video and stay tuned for more space related content. If you like the video, please hit the subscribe button and leave your feedback in the comment section.